lecture we shall start the working stress method. We shall start this lecture with the working stress method. Before going to the before going to the different that your actual method, let me give you that one the different steps of construction, just one schematic one. I do not know whether you can see, can you see this one, just a floor, okay. So, there are these are all three different say footing, because I have told you the construction. So, three different footing, the other three and other three. So, there are say 9 column footings, and we are having say columns, the second level and third level. So, that we can have, and this is that tie, these are all tie beams. So, we generally do not provide the, for wall we do not provide the wall footing, we start from this tie beam which will take the wall load. Also we can take it for the frame also, that connection, that also we consider, but we generally use it for say walls. And we have that beams, though we construct these beams and slab all together, whenever we cast these beams and slab, that all together, but just to show you that, otherwise I cannot show you, because if I keep that one, the roof, then we cannot see the beam. That is why I have made it. So, this is the one actually the construction how we do it. We have started from the bottom, but when we shall design we do it other way, we start from the top. So, slab, then beam, then column, then tie, then footing. So, this is the one during the your design will be there. Even if you have staircase, the staircase has to be designed first, we do design is first. So, this is the just only one schematic one. So, I should acknowledge here, because that particular program, and that is your POBRE. The program name is POBRE. So, I have used that POBRE, that one for this one. I thought okay, I shall use. This is a very free software, and I have found so far say so many softwares, rendering softwares available, but I have found this one is the so far the best one. Of course, my best thing always changes. That is another part. Anyway, so this one just to show you one example, you can also try. You can download and you can also try that different thing. You can try. Okay. Yes. So just to name it, I think I should write down POV. RAY. So, working stress method we are talking, and we should have the limits. Direct tension, I could write down in PowerPoint, but then I find that it will be difficult. So, that is why let us write down in paper, so that you also can copy. So, grade of concrete, because these are the limits we should know. And tensile stress, we have M15, though we do not use it, but M15, and the permissible stress is 2.0 Newton per square millimeter. M20, 2.8, M25, 3.2, M30, 3.6. There are so many others, but we shall consider M15, M20, M25, M30. Generally, we consider RCC that M20 and M25. So, our tensile stresses 2, 2.8, 3.2, 3.6, and this is from page 80, IS 456, 2000. Let me write down from. So, this is your the limiting values for concrete when it is under direct tension. When it is under direct tension, so these are the limiting values, and we shall mainly consider these two. So, we could remember it also 2.8 and 3.2. Otherwise, of course, it will be specified in the that examination, that your question paper. So, I can go to the next one. I shall tell you. Because we should know the permissible stresses, otherwise we cannot design. Permissible stresses in concrete, and this one will be in Newton per square millimeter. And we shall specify again that 4 grades of concrete only. And permissible stresses in compression. Permissible stresses in compression has two parts. One is bending, another one direct. One is called bending, another one is called direct. The beam, when it is bent, that is called bending compression. The compressive stress whatever developed, that is called bending compression. A column, whenever you press the column, say like this, you are pressing the column like this, then that is called direct compression. So, you have that bending compression and you have direct compression, two different that compression. And permissible stress in bond, and this one average. Also, we can write down, to be more specific, for plain bars. And those will be in tension. So, permissible stress in bond, average value for plain bars in tension. So, we shall write down the tension, and we have, we give it say sigma CBC that is your in concrete bending compression, sigma cc concrete direct compression, and tau bd. For M15 it is 5.0, direct compression it is less 0.6, M20 7.0, 5.0, 0.8, M25 8.5, 6.0, 0.9, M30 10.0, 8.0 and 1.0. This is, we have taken it from table 21, page 81, IS 456. You can see I have told that factor of safety about approximately 3. So, you can see 15 by 3, 20 by 3, which is coming approximately, which is coming the factor of safety 3. That means the cube strength here 15, 20, 25, 30, and you can get the corresponding bending compression in concrete almost 1/3. So, that means we are considering that factor of safety 3, that which I have told in the very beginning, that we are considering it here. Now, what about steel then? We have to consider for steel also. Let us give the permissible stresses in steel. So, permissible stresses permissible stresses in steel reinforcement type of steel, tension, compression, and we should have shear, because these are the different cases where you have to consider the permissible limits, or in other way that your freedom, that how far you can go. Fe 250, that is mild steel, Fe 250 is the mild steel. For that we have up to 20 millimeter dia, we have 140 in tension, 130 in compression and 140 in shear. Over 20 millimeter diameter, 130 in compression and again 130 in shear. That means 130 for all of them, 130. Only in tension and shear it differs if the bar diameter less than equal to 20 millimeter. Fe 415 high yield strength deformed bar, high yield strength deformed bar HYSD, high yield strength deformed bar HYSD up to 20 millimeter, it is 230, 190, 230, over 20 millimeter, 230, 190, 230. And this one we have taken from table 22, page 82, IS 456 2000. You can get it in this code, you can get these values, you can get these values in this code, but you should keep it in your exercise book also, because we require that one for our calculation. So these are the limiting values for concrete and for steel. Okay. So how shall we calculate the tensile stress? How shall we calculate the tensile stress? That again we can find out. The tensile stress equal to Ft divided by AC plus MAST, where Ft equal to total tension on the member minus pretension. This one we are talking that pretension, that I am coming to explain, if any. Pretension means actually that if you have any pretension and then you are applying the load, then you are getting the tensile stress will be increased. So that means you have initial value of tension, that way you can say. So that you have to, obviously you have to deduct it. And AC, cross sectional area of concrete, excluding any finishing material, excluding any finishing material and reinforcing steel. Only we are considering concrete. M, that modular ratio, M equal to that modular ratio, and AST, cross sectional area of reinforcing steel, to be more specific, in tension. So the tensile stress you can find out that Ft, you have to get it, and you can find out that Ft the total tension on the member minus pretension in steel if any. If the initial stress is there, tensile stress, that you have to deduct it. Area of AC means that concrete area, and obviously you should forget the finishing. Finishing means you should not take the plastering. The concrete cover, whenever we consider the concrete cover, say even if you give that say your reinforcement bar, if you can see the reinforcement bar from the bottom after cast the beam or slab, if you provide the plastering, it does not mean that you are giving cover. That cover, that is your say finishing material, not the one, it is not part of the concrete. So that's why we are very specific that we are not considering any finishing material, whatever you are using. M is the modular ratio, ES by EC that you can say, but our code does not take in that ratio, it takes in a different formula that we are coming next. And AST, that cross sectional area of reinforcing steel in tension. So
that is cross sectional area reinforcing steel of all the bars.
Yes, all the bars. We are considering that, always we consider that way. Even if we provide the reinforcement, that bar, so AST actually means that how many bars you are providing, the total area that you are considering. And we assume that one, we can say we assume that as I say, as a total one, I can say I am coming next actually, let me continue and then I am coming next to your point. So what is modular ratio, that already we know, but still let me make it clear. So modular ratio M that is called modulus of elasticity of steel divided by modulus of elasticity of concrete, and that one let us write down ES by EC. We also write down that our code says M equal to 280 divided by 3 sigma CBC. So we do not take it from ES by EC. Instead of that, we use this formula. We should remember this, where sigma CBC, that concrete stress in bending compression in Newton per square millimeter. So we are not going to that ES by EC. Instead of that, we shall take this formula, that, and on the basis of that we shall calculate M, how much we shall get. So that one we shall take say 280 by 3 sigma CBC, that we shall consider. So now we shall come to your point. Though we provide reinforcement, say like this, as many bars, how many bars would we provide say number of bars, but when you are considering say AST, whenever you are considering that AST, what we do, we can simply say like this, there is nothing wrong, simply we can say like this, that is the total number of bars, this one, as if that we can consider one plate also, because when we are considering that, so but that is at a particular point, and we generally consider that I have already told that effective cover. So effective cover, the thing is that if you design the beam, when you are going to design the beam, you do not know which bar you are going to provide, but you are calculating the area of steel. But at the time of calculating the area of steel or say effective depth, you need effective cover, and effective cover is nothing but that clear cover plus 5 by 2 the diameter of the bar. So, here what we do, we assume certain diameter. So, based on our experience, say okay, this is the moment. So, we know that this bar will come, whether 12 millimeter or say 16 millimeter or 20 millimeter, which type of bar diameter will come, that we can assume that, because if you do not many, even if you do 5 or 6 examples and then with the different say moments, immediately you can understand that what type of bars will come, because you do not have, finally if you consider at the end of the day, you will find out you do not have really, you do not have any choice, much choice. That means say okay, 250 millimeter is the width of the beam and you take certain depth, whether you will provide say 320 millimeter dia, 420 millimeter dia or 225. So, like that if you find few combination, you will find out that you do not have many choices, because whatever area of steel you can compute, because finally you have to provide certain regular number. You cannot provide something say 312.5 millimeter depth of the beam. You have to provide either say 300, 325, in that fashion only you have to provide at the say 1 inch, in that way you can say. So, when you have to provide that one, so that means you do not have much freedom. So, one can also do it that he can keep his all the beams, say possible beams ready, that moment of resistance, also the shear capacity he can keep ready, and immediately when you will get those say moment, okay, let us provide this one, let us provide this one. So, from the table itself we can find out, and we have actually one code also, that is that design aid, that SP16, that I have already told actually in the first class. So, from where also you can find out from the moment of resistance, calculate and provide the corresponding reinforcement, that area of steel, that also immediately you can compute. That way also your design also will be easier. What we shall do now, let us take one example. That we would like to find out a formula, and we are working on the working stress method. Working stress method. Let us provide just 2 bars. That depth, overall depth, we consider it as overall of depth. So, overall depth capital D, width B, effective depth small d, and strain is linear. So, epsilon CB, the strain in concrete in bending, that stress divided by modulus of elasticity, and epsilon ST, strain in steel, say FST divided by ES. This is our neutral axis. We should have the corresponding stress because since concrete does not take any tension, that is why I am not drawing the stress diagram here, because all the tensile forces will be taken care of by the steel only. So, this is your say T. So, FST times AST, the stress developed in steel, that is FST times the AST, that we shall get it, and FCB. Let us say this one, the depth neutral axis, so this is x. X is the neutral axis from the top, neutral axis from the top, and this force will be at the centroid of this section. So, C equal to area of this triangle half FCB times x, and we have definite say width also. So, B. Is it clear to you? So, we are considering the concrete, that compressive stress will be equal to the area of this triangle, and that one actually we can say this one, this is a wedge, triangular wedge type. That means this one having the along the depth also you will get it. So, half FCB times x or triangular prism, to be more specific. If we consider that one, that this is nothing but one right angled, that one prism, and that one we have to consider the volume, that one only will give you the compressive force. So, half FCB times x times the width of the beam, that is the total compressive force here, okay, and the tensile force, this one here, and this length, that is the lever arm. So, equilibrium, we have two equations. One we can consider here, that equilibrium of forces, after all it is a static case. So, equilibrium forces. So, tensile force equal to compressive force, that one should be there. So, equilibrium of horizontal forces. So, tensile force T equal to compressive force C. The lever arm we can consider this one as a Z equal to, we can write down one say fraction of say D. D is the effective depth. So, Z is nothing but obviously it will be certain fraction of effective depth, because this is the lever arm we are talking. So, it will be certain fraction of the effective depth. So, Z equal to ZD equal to D minus x by 3, this one x by 3, this portion. So, D minus x by 3 is your lever arm. So, this one will be equal to D effective depth minus x by 3, that one will be your lever arm, which again we can write down x, again we can write down as another parameter, say KD. I am assuming x is nothing but another fraction of the effective depth. You are considering everything in terms of say effective depth. So, another fraction say K. So, first one we have considered that j, another coefficient we are considering that particular one, say k. So jd is the one, the lever arm we can consider, and kd we can consider that one, that how much is, what is the your neutral axis, depth of the neutral axis, that we can find out as if that it is kd. We do not know k, neither we know k nor we know j, but we can write down in this way, which we can write down as d times 1 minus k by 3. So we can write down jd, that means j equal to nothing but 1 minus k by 3. So this is one important equation here, j equal to 1 minus k by 3. So effective depth we can calculate, and we can take a fraction that we have to find out. If we can find out either k, or if we can find out j, then obviously we can find out the other one also. So this is the one